Okay, I believe we are recording. So let's carry on. What I want to do first is continue in 6.2, which is the pigeonhole principle. So I want to give just more interesting examples of using the pigeonhole principle to solve interesting problems. And then probably at the end of this lecture, we'll start getting into section 6.3, which is on permutations and combinations. Okay, so remember the pigeonhole principle essentially says that if you have k plus 1 pigeons and you're trying to fit them in k holes, then at least 2 pigeons must end up in some hole. Very simple, very intuitive, but there are a lot of ways to use this in really clever ways to solve interesting problems. So as an example, let's show that given any, that for any n plus 1 integers less than or equal to 2n, there exists an ni dividing an nj for some ni not equal to nj. Okay, so the idea is you pick some n, and you pick all positive integer, you pick some positive integers, n plus 1 many positive integers that are less than or equal to 2n. One of your collection must divide a different one of your collection. Okay, so let's prove this. So first of all, let's write our integers a sub 1 all the way up to a n plus 1. These are all less than or equal to 2n. We use a prime decomposition. We use the prime decomposition, which is going to be write ai as being equal to 2 to the ki times qi, where qi is some odd positive integer less than 2n. It can't be equal to 2n. We can assume that it is odd because essentially I'm just saying take the prime decomposition of ai and lump all the 2's together, and then whatever's left over is a product of a bunch of powers of odd numbers because all the other primes are odd. So we can write every integer that is less than or equal to 2n in this fashion. Some power of 2 times an odd integer where the odd integer is less than 2n. Okay? So now how many odd integers are there that are less than 2n? And the answer is there are n odd integers that are less than 2n. N of them. This is something that you can prove for yourself, but there are some simple examples. For instance, how many odd integers are less than 4? Well, 2, 1 in 3. How many odd integers are less than 6? 3, 1, 3, 5, etc., etc., etc. So there are going to be n of these possible odd integers. So we have q1 all the way up to q n plus 1, which is n plus 1 odd integers. And they are being fit into a set with n odd integers. How do I want to say this? Right, so there are n plus 1 odd integers. These are the pigeons. And there are only n boxes, where the boxes are the number of odd integers that are less than 2n. So thus, two objects, two pigeons, must be in the same hole, which means qi is equal to qj for some I not equal to j. I can't have n plus 1 odd integers all distinct and all less than 2n. Two of them have to be the same. So we have ai is equal to 2 to the ki times q. I'll call qi just q. And then aj has to be equal to 2 to the kj times q. And it's clear that one of these divides the other. If ki is greater than or equal to kj, then ai, then aj divides ai, and if kj is greater than ki, then ai divides kj, right? All I need for this number to divide this number is for this coefficient, or this power, ki, to be less than or equal to kj. That's all that's required for dividing. Okay? Any questions on this? And phenomenal. I have not set a timer, so I have no idea how long I've been doing this. Let me start now. I'm going to assume that took me 7 minutes. We will see how close I was. Okay, so we have proven this one using the pigeonhole principle. Let's go further. So for this problem, this is a semi-famous theorem that I believe was proven by Erdős. At least I've heard it cited. Erdős, a Hungarian mathematician of the 20th century. So what this is about subsequences. So given a sequence, a finite sequence, say AI, a subsequence is basically you just select some members of your sequence and you preserve the order. A subsequence is a subset with the induced order. So for instance, if I have a sequence that looks like 1, 10, 9, 5, 7, 11, then some possible subsequences are 1, 1, 10, 9, that's a subsequence. Let me put semicolons in between these. 10, 7, 11 is a subsequence. 11 is a subsequence. I don't know. 511 is a subsequence. So all that you're doing is you're picking a couple elements to be in your subsequence, and you just read them in that order, essentially. Then you get a subsequence. And a subsequence is increasing or decreasing, or strictly increasing or strictly decreasing in a natural, reasonable way. So for instance, the subsequence 511 is strictly increasing. The sequence, well, none of these other sequences are either increasing or decreasing. They all kind of go up and down. But anyways, so now we have a definition of a subsequence, and we know what a strictly increasing subsequence is or a strictly decreasing subsequence is. So let's prove the following fun theorem. So theorem, and I believe once again this is due to Erdős. Every sequence of length n squared plus 1, consisting of distinct real numbers contains a subsequence of length n plus 1, which is either strictly increasing or strictly decreasing. Okay. Let me just do an example where n squared is going to be, let's do n is equal to 2. N is equal to 2. So I'm going to pick five integers, or not, sorry, 5 real numbers, like negative 1,000, pi, e, 3, 500. What this is saying is that there must be some subsequence of length 3, which is either strictly increasing or strictly decreasing. In this case, I think there are a lot of subsequences which fit the bill. There could be more. So for instance, here is a strictly increasing subsequence. Negative 1,000, 3, 500. Okay, so this is a length 3 subsequence which is strictly increasing. There is not a length 3 strictly decreasing sequence in this particular example. So all the theorem is saying is that you must have one of them, either strictly increasing or strictly decreasing. Okay, here's the proof. So to each element ni, or ai, sorry, actually I do want to use ni. To each element ni, we attach an integer pair ai di, where ai is the length of the longest strictly increasing sequence starting from ni, and di is the length of the longest strictly decreasing sequence starting at ni. So let me do this example for these. For 1,000, I'm looking for the longest strictly increasing sequence starting at 1,000. And I think that's going to be 4. I can do 1,000 e 3 500. So I have a sequence that's increasing of length 4, and then I'm looking for a sequence that decreases. Well, all of these numbers are bigger than negative 1,000, so this is just 1. The longest decreasing sequence starting with negative 1,000 is just the subsequence negative 1,000. Let's do this for pi. Strictly increasing, well, e is smaller than pi, and 3 is smaller than pi. So if I want to increase starting from pi, I can only do pi and then 500. So 2. And then if I'm decreasing, either pi e is decreasing, and also pi 3 is decreasing, but pi e3 is not decreasing. So the longest decreasing sequence starting from pi is length 2. Similarly, e, well, e3 500 is strictly increasing, so I put a 3 there, and then all these are smaller than e, so I put a 1 here. Similarly, 3, I have a 2-term increasing subsequence and only a 1-term decreasing subsequence, and 500 is 1 and 1. Okay, I just wanted to do this example so you see what numbers I'm associating to each term in my sequence. So our proof goes as follows. Assume, for the sake of contradiction, that no no SI or SD, no strictly increasing or strictly decreasing subsequence has length n plus 1. Okay, if no increasing or decreasing subsequence has length n plus 1, this means that 1 is less than or equal to AI and is less than or equal to n for all I, and 1 is less than or equal to DI less than or equal to n for all I, right? If either AI or DI is n plus 1 or bigger, then that's telling you there is a subsequence of that length that is either strictly increasing if it's AI or strictly decreasing if it's DI. Okay. But there are there are n squared possible tuples, AI, DI, with the above conditions. And n squared plus 1 n squared plus 1 terms of the sequence. Right? In this case, if we assumed that, let's do an example here. Let's say that we picked a different 5-term sequence, and then we assume that there is no increasing or decreasing subsequence that is of length 3. Then the only possibilities would be 1, 1, 1, 2, 2, 1, or 2, 2, right? These would be the only possible options if I have a 5-term sequence and both terms are greater than or equal to 1 and less than or equal to 2. But I have 5 numbers. By the pigeonhole principle, we must have AI DI is equal to AJ DJ for some I not equal to j. I've only got n squared possible tuples, and I've got n squared plus 1 terms, so 2 of the tuples have to be the same. Then we get a contradiction. Because either ni is less than nj, or ni is greater than nj. Remember, we assumed that all of the terms of our sequence were different. If ni is less than nj, it's not possible for their longest increasing subsequences starting at that term to be the same length, because let's say nj has term ai equal to some number. That can't be the same as this number because I can always build a new sequence starting with ni and then continuing on with this subsequence, right? Like these two numbers, if this is the case, ni, nj, I can always take the subsequence starting at nj and make it longer by adding ni on at the front piece. Similarly, if ni is greater than nj, their decreasing sequence lengths can't possibly be the same because I can take the decreasing sequence starting at nj and make it longer by tacking on the decreasing sequence starting with ni and then going ni, nj, and then the rest of the subsequence. So in this way, we get a contradiction. It's not permitted for two different integers or two different numbers to have the same tuple of integers. Okay, that one might be worth thinking about for a little while, and if you have any questions, please don't hesitate to ask me. But that's a fun use of the pigeonhole principle to prove kind of a unexpected or surprising fact. Okay, great. Let's continue. Here's a fun one. Let's do the following example. Let xi and yi for I is equal to 1, 2, 3, 4, or 5. I is inside the set from 1 to 5. So essentially what I'm doing is I'm picking 5 points, be 5 distinct points with integer coordinates in R2. So essentially I'm just saying pick 5 points in R2 such that the x value and the y value are both some integer. Show that the midpoint of some line joining 2 points must have integer coordinates. So what this is saying is, let me pick some examples. Let's say I took 3 points, say 0, 0, 1, 2, and let me see if I can figure out one where this doesn't work. 0, 0, 1, 2, and I guess I want 2, 1, maybe? 2, 1, right? If I draw my grid, so I picked 3 points, all with integer coefficients, and it looks like none of the midpoints of the lines is an integer valued point, right? This point isn't on the grid, this point isn't on the grid, and this point isn't on the grid, in the sense that the midpoint of the line joining these 2 points has coordinates 1/2, 1. The midpoint joining these 2 lines is 1, 1/2, and the midpoint joining these 2 is 1/2, 1 and 1/2. So here I picked 3 points, I took all the lines joining them, and I found that none of the midpoints had 2 integer coefficients, had both integer coordinates. What this example is saying is, if I took 5 points that were on the integer lattice, and I took all the lines joining them and I looked at all the midpoints, at least one of them must have, at least one of the midpoints must have integer coordinates. So let's do a proof. So note the midpoint of, the midpoint of xi, yi, and xj, yj, well, we know the formula for the midpoint. It's just going to be the averages of both of the coordinates, is xi plus xj over 2 and yi plus yj over 2. Okay? So the question is, when are both of these numbers integers? And both of these numbers are integers whenever xi plus xj is even and yi plus yj is even. Now, when is the sum of 2 numbers even? The sum of 2 numbers is even either when they're both odd or they're both even. right? So essentially, what I'm saying is that there are four options. Or what do I want to say? Yes, what I want to say here is that this tuple has integer coordinates if the xi and the xj are both the same parity and the yi and the yj are the same parity. So this point has integer coordinates if xi, xj have the same parity and yi and yj have the same parity. So what we should do now is we should check what are the possible parities that can appear if I take a pair of integers. I take a pair of integers, what are the possible parities? There are four possible parities. There's even, 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 odd, odd, even, and then odd, odd. Okay? So if I choose 5 points, 5 integer coordinate points, two of them must be in the same basket. Which means if I pick 5 tuples of integers, I must have at least 2 that are in the same one of these 4. I have to have 2 numbers that are both even, even, or I have to have 2 numbers that are odd even, right? Notice that this did not happen in my example. Here I had even, odd even, and even odd, right? If there are 3 elements, then I can put them all in baskets such that no 2 share the same basket. But if I add 2 more integer points, for instance, something like 5, 4, and 6, 7, well, now I have even, odd even odd, odd even. So now these 2 are in the same basket, and then this is even odd. These 2 are in the same basket. By the pigeonhole principle, I know that 2 have to be in the same basket, but the point is that the midpoint of the line joining these 2 has to be an integer coefficient point. And similarly, the midpoint of the line joining these 2 has to be an integer coefficient point since we have the same parity. Even, odd, 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 even. So if we choose 5 integer coordinate points, 2 of them must be in the same basket. Thus, xi, xj have same parity, and yi, yj have same parity. Thus, the midpoint must have integer coordinates. Okay, let's do one more example. These pigeonhole principle problems are so fun, so let's just do one more. Example. How many numbers must be selected from the set 1, 2, 3, 4, 5, 6 so that at least one pair adds to 7. Okay, This is going to be another pigeonhole principle thing. What we're going to do is we're going to look at the following. What are the possible pairs of this set that add to 7? Well, 1 and 6 add to 7, so I'm going to make one subset consisting of 1 and 6. 2 and 5 add to 7, so I'm going to make another subset consisting of 2 and 5. And then lastly, 3 and 4 add to 7, and they're both subsets here. So the real question is, how many integers must be picked to force two of them to be in one of these subsets? And the answer is 4. If 4 integers are picked, and there are 3 possible baskets, two must be in the same basket. Right? Like, I can pick 3 integers from this subset such that no pair adds to 7 by picking 1 from each subset. If I pick 1, 5, and 3, well, 1 and 3 don't add to 7, 1 and 5 don't add to 7, 3 and 5 don't add to 7. But the moment that I pick 4 integers from, once I pick 4 integers that are coming from 3 sets, then 2 of those integers have to be in the same set, and once I have 2 integers from the same set, I know that I can add them to 7. So if I pick 4 numbers, for instance, 6, 2, 4, yeah, let's say that I pick 6, 2, and 4, then any other number that I pick has to be one that'll add to one of the ones that I already have to 7. If I pick 5, then 2 and 5 add to 7. If I pick 1, then 1 and 6 add to 7. If I pick 3, then 3 and 4 add to 7. And you didn't have to start off by picking 6, 2, and 4. But this is just to kind of show how I'm using the pigeonhole principle here. So the answer here is 4. I have more exercises involving the pigeonhole principle. Why don't I just leave this one as a challenge exercise? So prove that at any party, where here parties involve 2 or more people, prove that at any party there are at least 2 people who know the same number of people at the party. And here I'm assuming that knowing someone is symmetric. So if person A knows person B, then person B knows person A. Yeah, this is a challenging pigeonhole principle sort of problem. I would say that here's a hint. You want to assign each person the number, each person ni, the number of people that they know. Which will be some number ki. So person 1 maybe knows 5 people. Say it's a party of 10 people. Person 1 maybe knows 5 people. Person 2 maybe knows 0 people. 0 is an option here. Person 3 maybe knows 8 of the 10 people, right? You want to assign each person a number, ki. The hint number 2, if the party has n plus 1 people, you cannot have 0 equal some ki and have n equal some kj. So what does it mean if 0 is some ki? 0 means a person doesn't know anyone else at the party, but n being some kj means that person j knows everyone else at the party. And since knowing someone is symmetric, it's not possible for one person to know no one and for someone else to know everyone. You can think of this in terms of graphs. Someone who knows no one is an unconnected node of the graph, right? Here, knowing someone is represented by a string or a line joining the graphs, right? So this person knows 0 people, whereas this person knows 2, this person knows 2, this person knows 1, and this person knows 1. Whereas, on the other hand, in this party, which is an interesting party, this person knows 4 people. If there are 5 people and one person knows 4 people, it's not possible for any other person to know 0 people. So this is hint number 2. Yeah, I think those 2 hints should get you started on this interesting problem. I won't necessarily make it do for homework, but I think it's a good one. Okay, so these are a bunch of much more interesting examples of using the pigeonhole principle. Thanks for listening.